Those of you who haven't just been to Florida, some of you have been to Florida, everybody else is going there now. Is there now? Are you going back to Florida this week? No, that's enough. Well, I was right in thinking that 25 copies would be more than enough. You ought to get extra bonus. You ought to get an extra bonus for being here. Yes, yeah, that sounds, okay, wait. We're going to have we're going to have a quiz here. But sign attendance. Here's a page of sign attendance. This is a positive. This is a positive thing, not negative. It's positive. Yeah, I don't know. Sign that you're here. This is supposed to be good, but maybe bad. In other words, one of the great problems with this course and this stuff is it's very unreal. And, and the problems are not inspiring because they're so simple they don't relate. It's not convincing at all that they relate to real problems. And the reason for that is actually the real problems are pretty hard in every possible dimension, as you may find, as you're maybe well aware of from other courses, where maybe if you do a project course or something, everything's extremely messy and you're spending all term to work on some problem with a team of 5 or 6 people or something, and you're dealing with some problem. But somewhere in the middle of that thing that's not the whole team is trying to actually address some methodology to address a real problem. And that's what these 2 papers have to do with that. So on the one hand, these papers connect to what's in chapter 5 of Ross. And on the other hand, they connect to real problems. And how would you use one of these continuous time Markov chain type models to do something important or useful? Not earth-shaking necessarily, but reasonably useful. And it's typical of operations research. It's a kind of issue that would occur in lots of settings, so it's reusable. I mean, you could be so in particular, the general setting is these models. So we might have something like this, and then we have these parameters. And this is actually sometimes known as the Erlang A model. And then if this is not here, this Erlang C model. These models, this abbreviation, as I discussed before, is notation for queuing models. And these are both continuous time Markov chains, and they're birth-death processes. So this is chapter 6, which we've already talked about. This is saying the arrival process is Poisson at rate lambda. The service times are exponential at rate mu, mean 1 over mu, and they're S servers working in parallel. And then this says that there's customer abandonment, and each customer abandons when he's waiting, not in service, but waiting customers abandon at rate theta. These rates are the things you put in the Q matrix of the continuous time Markov chain. Everything's happening probabilistically, but these rates, and you only have, this model has only 4 parameters, and this one has only 3, S, lambda, and mu, S, lambda, mu, and theta. So it's a kind of manageable model, only a few parameters, basic queuing models, classic queuing models, going back to Erlang, who worked on these things almost 100 years ago. Erlang was an engineer for the Danish telephone company, and he worked on queuing models, these models, 90 years ago. Wrote papers on them and did amazing stuff. So the stuff is there 90 years ago, and a lot of this problems that I want to talk about existed then, and they still exist today. And and maybe in some ways Erlang knew a lot more 90 years ago than most people know today. That's fortunate. That means when you learn this stuff, you have value added in the marketplace, because even though Erlang discovered it, just like a lot of the techniques you're learning, even though Danzig discovered linear programming, when you learn it, most of the people you interact with aren't going to know it at all, and you're going to provide value added. Right? I mean, because you're going to know stuff, even though you didn't invent it, you're going to know technology that is useful. Now, these are the standard models. Now, the real problem, is staffing a service system. And if you look on, you'll see the thing I've been focusing on a lot is call centers. Okay, I happen to be doing, if you look at my web page, you'll see I'm doing a lot of stuff on call centers and on these models. So I'm interested in call centers, and I visit call centers, last year I was consulting for Avaya on their call center products and stuff. So this is an area where I work, and then staffing is only one issue, but then it should be fairly easy. This is a problem that actually is fairly easy to understand and real, and it's got, so the standard, the oldest problem was actually designing a telephone exchange. That's what Erlang was concerned with. So he was concerned with, first, if you have a switch, how many lines should you have, with the various subscribers and so forth? So, how much equipment did you need? But the problem that's related to this is the old problem, which maybe I remember, but most of you do not. So in the olden times, actually, at some point, when you made a telephone call, you actually did so through an operator, because there wasn't automatic dialing. So they're actually, at an early point, they actually had what would today be call centers for other things, were operator groups that responded to every call. If you wanted to call, they would connect you. So maybe they wouldn't spend too long. You'd call, and they would, you want to do this, and they put the cord here, and they're doing their little thing, and you're only there for a short time. Or if you call now for information, it used to be very common to call information, but that's kind of automated, not too much. But all that telephone stuff disappeared, right? There's automatic dialing. A lot of that stuff is reduced, and yet people doing the same function in call centers. So if you want to get anything, if you want to get a reservation, if you want to get a plane ticket or a train ticket to get out of here, soon, today, or if you haven't done this already, it might occur to you soon. You're gonna probably call a call center. So I mean, you interact with we do a lot of business on the phone, and you're calling, and there'll be 400 people working in some building responding to these calls. And one part of this problem is how many people, how many agents should you have there to provide the service that is going to be required? That's the issue that I'm trying to deal with, and you can use the queuing model. So the question here, roughly speaking, is how big should S be? Right? That's the kind of real decision problem. You're going to do this system. So now, actually, this problem, there's a lot of steps in this problem. If it was a call center, you first of all have to decide what's the capacity of, how big is the building, how many seats are going to be there for the agents, how much, equipment. There's a lot of this very fancy equipment, so you're going to need automatic call distributor that distributes all these calls to the agents, but you're going to need databases and computers and seats for the people to do this work. So you're going to kind of set the capacity. Then you're going to have to train all these people. You have to hire them and train them. So you're doing all that stuff. There's all this. Then, for each day, you need to know how many people do you need. So you kind of, staffing means setting staffing requirements. Just really means, in the context of one of these problems, how big should S be? Okay, that's sort of the issue, the problem. The problem is this. That's the one I want to look at. However, the thing goes on, there's more issues, right? I mean, having picked a S, you need to schedule the people in the various shifts and throughout the day. And that's typically done with a linear program, integer linear program. So you're doing the math programming, there's usually a scheduling algorithm that involves math programming that takes if you need 100 agents, you're going to somehow work tours of duty out for all those people, specific times they're going to be there. Maybe it's 8-hour shifts with designated breaks and lunch periods and so forth. So you have to do all of that. So the staffing, there's capacity, hiring, training. That's all in the long time scale, long. Then there's staffing, which is just setting S, the requirements. But then there's scheduling, but then there's adjustments. Somehow, if things aren't working right, you're going to change somehow on the fly during the day. Maybe you're going to do that too. And the whole thing has got a lot of steps to it, right? So that, and I'm just thinking this step, and the reason for focusing on that step in part is that's the step that's precisely queuing theory. The scheduling is math programming. This is some sort of manager watching what's happening. And this stuff is some other kind of optimization, long-term planning. Sitting in here is forecasting. So somebody has done in the background at this close to this issue is forecasting. So that's what is lambda? What is the arrival rate? And somehow you know what's the mean service time. So these parameters are estimated and you somehow forecast what are the arrival rates going to be. So you're actually fitting this model, the lambda mu theta, you kind of estimate all that from data, and then based on how big lambda is, you want to find S. So that's, I'm contending that that's a sort of real problem where you're going to use the stochastic model. And the stochastic model enters in because it's not just a function of these things as if they were deterministic. If they were deterministic, there would be no, the staffing requires to adjust for fluctuations. There'd be something on average, but there's some fluctuations. The fact that you have weighting and so forth is because there's random fluctuations. The arrivals are actually random. They don't come at a constant rate lambda. The service times vary. Some are short, some are long. And the fact that this is a stochastic model very much determines what happens. So you want to, the stochastic model is the stochastic component is very important for determining what S should be. So if you somehow have, on average would need 100, maybe you have to have 115 to hedge against the fluctuations that occur. So that's what we want to deal with. Now this is what's in the book, mostly, in all the books, is this. Now the thing I want to talk about isn't that, right? It's more real. So there's a point here where this stuff that is in the book is a total disconnect from reality. Okay? And this is the kind of problem that you frequently have, because you'll get some problem, and this problem just doesn't connect because it isn't compelling. It's not real. Real thing's totally different. The real thing is totally different from this in a fundamental way that I want to talk about today. I haven't got there yet. Looks like I'll never get there. But I think that more than the details is the point of the thing of sort of what I'm trying to convey is a flavor of how this stochastic probability models do get applied in practice rather than the details of one of these small problems. Okay, now what do I want to emphasize something that's missing. So let me do that by drawing a picture. It's not like this. The question is, what's this? Okay, you're okay with that, but the question now might be, this looks a little bit like the picture in the Prince. But anyway, forget that reference. Question, what is this picture? This is the reality. That in the Prince, it's the thing they swallowed the snake swallowed the elephant, ate the elephant, right, or something. Okay, but anyway, it sort of looks like this. That's just a real reaction. Okay, but anyway, what is this thing? So I'll give you some hint. I'll keep giving you hints. Okay, what is this thing? I've added something. Yeah. Wait, I heard it, but I didn't know where it came from. Who made the utterance, the quiet utterance?
Like arrival rate?
Yeah, thank you. This is arrival rate. Yes. The real arrival rate to a call center, to a bank, to an airline, any place, any service system, looks something like this. I mean, in the middle of the day, it's high, and at 3 in the morning, in New York at 7 in the morning, it's low. In the rest of the world at 2 in the morning, it's low. Okay, whatever. Somewhere this is really low. The arrival rate's low, and sometimes it's high. This is kind of like, in the morning, in a business, there might be a peak, and after lunch, there might be a peak. If it was a bank, it might actually peak in the middle because people are going there in the lunch break, right? But this is sort of like some business thing. If it was a financial services call center, where people are calling in to do buy and sell stocks, if maybe they're mostly doing it online. But if you were calling, if it was a business thing, you might call, if you want to complain about your bill on the phone. That's sort of a typical case. And you call not during lunch. You have lunch during lunch, okay? But you call in the morning. So this might be 10 a.m., and this might be, 2 p.m. And maybe it does something, and then maybe it's it's maybe a 24/7 call center, but it still has this strong thing. So that's the reality I want to talk about. And all the things, almost everything in basic stochastic processes and queuing models, all these books, if you pick up a book on queuing theory, the odds are the entire book will look like this. There'll be all these models. I mean, they may not use this notation, but there'll be MMS, MGS, MG2, and they go through all these models with variations. They'll all have the property that the model's stationary. And what they're going to tell you, right? What questions are we answering? We're always asking, what's the steady state distribution, right? You make up a model and you ask, what's the long run behavior? You run the model forever, and what's the long run behavior? You solve pi equals pi p because p, the thing goes along according to p for a long time, and then you solve pi as the long-term thing, and you solve alpha q equals 0 because when it runs for a long time, alpha is the long-run proportion of time you spend in each of the states and so forth, right? This thing isn't that, right? This is the real world. It isn't that. That's the point. And so and knowing that, and you all know that, if you thought of any service system you deal with, the arrival rate looks something like this, invariably. And therefore you think, what's the point of this, right? So one reaction would be, this is a reference point, and you could simulate the thing, the real thing, right? So if you take simulation, it would be routine and standard if you take simulation. Here, one of our simulation courses, that you would do a project like this where you would actually do your simulation and their daily arrival rate pattern would look like this. And that you'd do that would be natural for a simulation, no problem. It's sort of interesting in the book. So if this is the arrival process, this is just an aside. I'm going along. Suppose you were doing a simulation, and this is the arrival process. So this is really lambda of t, because it's not constant. And now you're doing your simulation. And you want to generate in your simulation arrivals according to this. How do you do it? So actually, you should know how to do this, or you should be able to think of it now. How do you do this? Okay, this is totally off the top of my head, but you're doing a simulation, and you want to generate the arrivals. So you're going to somehow, they're going to be random. They're going to be a Poisson process, a non-homogeneous Poisson process, which is one of the topics you're going to be reading about in Chapter 5 at the end. This is a non-homogeneous Poisson process. The arrival process is a Poisson process, but with time-dependent arrival rate. And now you think, well, I want to simulate that. Well, see, do we know how to simulate a Poisson process? Not so clear, but it ought to be not hard. Suppose it's a homogeneous Poisson process with rate lambda. Well, we know the times between arrivals are exponential, independent, identically distributed, exponential. So we want to generate a regular homogeneous Poisson process. All we have to do is we take a uniform, and we take minus log uniform, log uniform on 0, 1. So log uniform is negative, minus is positive, multiply by the mean. This thing is exponential. So I'm just, turns out if you start with the uniform and you look at the log and you calculate what is the distribution of this thing is exponential with mean m. So you generate a whole bunch of uniforms. When you go RAND, whatever language you use, you generate a ton of uniforms. You just say, generate 10 to the 6 of these guys, these suckers. Do this for each one. Do it in the MATLAB. Do it all in one command, because you just do it in vector. You generate 10 to the 6, a vector of 10 to the 6 of these. Do this to every term of the vector. You've got 10 to the 6 exponentials. You let the cumulative sums, and you let the cum sums, and that's right. And the cumulative sums of those exponentials are the points. That's it. So you generate a vector of uniforms, transform it this way, do the cum sum command. You've got 10 to the 6 arrivals, standard Poisson process. Right? Like 2 or 3 lines. For me, 3 or 4 lines. For you, maybe 1 line. Right? Remember, the dinosaur versions, 2 or 3 lines. Okay, not hard. Now, what about this sucker? The inter-arrival times are not exponential. Things a mess. However, you know just what to do with this. You generate your first Poisson process, as we described, the homogeneous one. Up here, you generate it with this rate, some lambda. Boom, like that. Now, what you're going to do is you're going to thin this Poisson process. Remember, if we independently thin a Poisson process, we get a new Poisson process. And this will be in Chapter 5, this thing. So if you thin here, P at t is going to be lambda t over lambda. At this time, t, P of t, we're going to say any point that occurs in this Poisson process at this time, I'm going to count it as a real point with this probability. Right? I generate the Poisson process at rate lambda. At every point that occurs, there happens to be one here. I count this one as a real one with this probability, independently of everything else. That produces this Poisson process. Boom. Right? You just independently take the points and, as a function of time, select them. And you thin, but you thin in this time-dependent manner, and you produce this non-homogeneous Poisson process. And you're ready to go with your simulation. That's useful to know. You've now got the thing with just a little bit. You've gone from the homogeneous Poisson process to this one. Okay, well that was an aside, but this is sort of reality. So simulation's certainly a great tool. I mean, this course is not about simulation, but that's certainly a fine way to proceed. This course is about doing it analytically. thinking about it and producing formulas and somehow figuring this out, figuring out how to do this with a simple method. Yeah?
Can you also do it by picking a majorizing function?
Yeah, that's what this is.
But one that's closer to...
Oh, yeah, you could be doing this one. You could say, well, here I'll use this. I'll generate it for here with this Poisson process, and here I'll generate this, and then here I'll do this, right? And I could do it better, and I would waste less effort, because I wouldn't have to do so many of these, because down here I'm going to generate, right? Totally, you could be doing this piecewise with just some one that was closer, and you'd then be more efficient. Definitely, right? It would be much more efficient to do this with this lambda here, and then this one here, and then this one here, and then down here. And just do them separate pieces if you wanted. That would really help a lot, like over here, right? Good point. Okay, well, that's, I'm not really worried about this, but it seems like it's nothing wrong with wherever the Spirit moves us. 24/7 is still there, I guess. Okay, so so what we really want to do here is we have one of these models. So this is the most general one. Let me get rid of this one. The real world is not quite this, so we want to soup this up a little bit to make it relate to the real world. So the first thing we do is we make this time dependent instead of constant, like that. And we make the service times general according to some CDFG. Because in call centers, when they take data, the stuff isn't exponential, it's log normal, say. Whatever it is, you can go measure it in your system, in your service system. What's the service time distribution? Collect a bunch of data, what is it? Find out what it is, not only its mean, but whatever distribution it is. If it's nearly exponential, fine. If it's something else, use that. So you now have this MTGS. And what usually happens is the service time distributions aren't the same at all time, but they tend to be mostly the same. They change slowly. So the service times at night are different than the day, but they don't change as fast as this. So it usually suffices to think of the service time as not depending on time. So this is no longer this, or it's the time varying. Now, once we put this in here, we've made this thing really hard, because this G, if it's not exponential, this thing's not Markovian. When you make the T in here, it could still be Markovian, it's just time dependent. But once I make the service times have general distributions, there's a whole bunch of people in the system with different service time distributions, and the evolution in the future is going to depend on the past, because you don't have the lack of memory property if they're not exponential. So you may have 100 servers, say you have 100 people in service and maybe 5 waiting. What's going to happen in the future? Well, the distribution in the future depends on, for each customer, how long they've been there. So it's a very complicated system. This is the point where people say, trust me. This is the line, the operative line. Trust me, this is a hard problem. That usually means there's got to be something wrong with you, what I just said, right? When that's at least my response to this. Anyway, that's an operative word, right? Trust me, this is a hard problem. Anyway, it is a hard problem. Okay. Okay, so we really now are interested in this. I'm assuming. This too. So there's some distribution, a function, not too many parameters, a function now instead of one number, a function instead of the mean, and a function instead, these are the CDFs, so functions, so now the thing's getting messy. So the parameters are now functions instead of numbers. So instead of 3 numbers, I got 3 whole functions as parameters. But once I make these, even if it was stationary, the thing's notoriously hard. right? Even without this is a killer. And in fact, nobody knows how to solve this problem. I mean, simulation is not put back by this at all. Simulation can go right through this just the same as the other one. So that's why simulation is great. However, there is something you can do, which is the point of, this may only end up as motivation, but the 2 papers I gave you are about what you would do with this, or what you can do with this. Okay? So, and there, and there's a simple idea that has to do with opportunity. This is typically the way operations research or problem solving goes. When you're looking for a model, part of the issue is what's real. No doubt about it. Part of the issue is what's real. But the other part of the issue is what can you do? In other words, what tools do you have? That's an important feature. That's why you learn all this stuff, even though the problem's stupid, because you want to have this bag of tools so that when you come to a problem, you could say, well, which of the tools I know work? I mean, so there's actually a good tool here. And if you know that tool, then you realize you go for it. But if you just go at this is realistic and this is hard. So what the point I'm trying to make is there's a nearby model that's not hard. And actually, you're learning about this model in Chapter 5. I mean, it's there in Chapter 5. It's easy to pass it by as one of the more complicated things that I'll just put off until later, right? So I'm trying to sell this one as worth just being aware of. It's actually there in Chapter 5, but it's easy to think. I mean, a lot of Ross has these examples that are a little bit hard, and then you think, well, this is second order. You know, it's a little difficult. And it sort of comes to, it's like physics. You want to think of a model that's an idealized model that's somehow going to do the job, and the model may not look like it makes any sense at all. I mean, your goal here, well, a goal might be to find not just S, but now that it's time varying, I want S of t. I want the staff as a function of time, right? Given that I've got this arrival rate function, I'm sort of roughly expecting, I'm thinking I'm going to staff, well, not that, but something, my staffing schedule might look like this, roughly, right? The arrival rate looks like this, the staff something like that, in relation to this in some sort of simple way that I'm going to, at least the staff is going to somehow adjust according to this arrival rate. So I'm actually now, the problem is no longer this, but it's this, and then the question is, what is this function of time? So the problem is actually much harder. First of all, the problem's harder because I've got time-dependent arrivals, but now the question's harder because I want a function of time, not one number. And if you were simulating, the problem has all of a sudden become a lot harder. Because maybe here, if there's normally could be 100 or 400 servers, and they could be varied, at each time, maybe you staff constant. You only change once every 15 minutes. The other bit of reality is that there are staffing intervals. You don't change constantly. You only change every 15 minutes or every half hour or whatever. And if you have only a few agents, maybe you only change once a day or once every 4 hours or something. But if you have a lot, you can usually change every 15 minutes. But, so suppose you change every 15 minutes. At one of these 15-minute intervals, there might be 20 candidate staffing levels. And there might be, well, let's see, 24 hours in a day, about 100 15-minute periods, right? So we need, in each of the 100 periods, time periods, 15-minute intervals, 24 hours, 4 times 4, 96, each in 100 15-minute periods per day, there might be 20 possible staffing levels we'd consider. So how many staffing functions altogether are there? 20 at each time. A few. So when you're going to solve this problem by simulation, And if you were going to look through all these cases, if you don't do it in some really, if you don't insert some cleverness, if you're going to do it by brute force, you're going to look at all these, which is going to take you a while. It won't take you long to simulate any one case, but it might take you long to examine these, right? So actually solving this problem by simulation, once we want to know a function instead of 1s, this problem became a whole lot harder. It's not so simple. 1s, sure, simulate the thing, right? 1s for this whole thing. Just simulate the 10 cases of s that you might consider and write the simulation. 1s, if you want to find it, do it for about 10 different s's and find the one that gives you what you like. No problem. But now you have 20 to the 100 possible staffing functions you want to consider. A little harder. Okay. There are practical things, and there are things you can say about it. Now, it turns out that, and it's the punchline is in front of you, obviously, but it turns out that there is a way to approach this that involves using a good model. And the model doesn't look right. So the model you use everything looks right. This is lambda t. This is that CDFG right here. Same stuff. No change, except here. Now the point I want to make is this looks really stupid. This requires kind of what they say out-of-the-box thinking. It's reasonable that this seems stupid, right? Because we're really focused, the problem we're really interested in is finding out the number of servers. The servers there, this number is the critical part of the problem. If we turn around and assume that there are infinitely many servers, surely we've thrown away the whole problem. Right? I mean, at some level, it doesn't look right. You wouldn't think of doing that because the real problem's gone away. However, in this model, you might think in the real model, you want to know that the number of customers in this, you want to know that you have to wait at time t. In the real system, let's say we want to know at time t, what's the probability that I have to wait? That's the probability that the number of customers in the system at that time t is greater than the number of servers. Then if some new arrival comes at t, he's going to have to wait. Now here, this is this real thing, so I could call that real. Then I could instead look at this, where this is from this model, in the infinite server model. Doesn't behave quite the same, but I'm now saying I'm going to look at the probability that the number of busy servers in the infinite server model is bigger than this level. This has nothing to do with this. This is the number in the other model. This is the number I might consider, right? But infinite server this is a level that I'm interested in. So I'm thinking in the infinite server model, what's the probability that the number of busy servers is bigger than some level? That's what I'm going to think of as my real delay probability. The probability that somebody at time t coming in would have to wait. That's this. Number of people in the system is greater than the number of servers, and if somebody arrived at that time, they would have to wait. But this is the same thing, except this is from this other model. This is just some level because there's all these servers there. Now, if there are quite a few servers, the feeling you ought to get is, this takes a while to absorb, but if there's a lot of servers, the distinction of what happens when the few of them are, whether, if there's 100 servers, it's the same in both systems, because when they're in service, they're in service. But when they're waiting, this thing doesn't have them waiting. This system has them entering service as soon as they arrive. Whereas this other one has them waiting or abandoning or doing something else instead of starting service immediately. So it's not quite the same. Okay, but that's not why you do this. You do this because this is a bit of unreality. You do this because it's going to really buy you something. you choose this alternate problem that's an approximate problem. This is not the real problem. The only reason for distorting the problem is because we can solve this one and we don't have a clue how to solve the other one. That's just like when you make a linear program and the thing isn't linear, but you make it linear anyway because you can solve it, right? It's just, all these things are exactly that thing. The reality isn't that. This is just another instance of that. Only this hits you in the face a little heavier, linear, but when you make a linear program model, the stuff in reality usually isn't linear, but you force it. You try to, some way, if you need to, you do quadratic, separable cone programming, some other thing that the guys downstairs do, other guys do. Okay, so the real issue here, the real thing then is that there is a good news for this model. That's the key thing. This thing, amazingly, this model has a very simple distribution. Not just a distribution in steady state, but because steady state doesn't exist. This has a simple distribution at all times t. It's one of these things where the best possible thing in the world happens. It's totally simple, everything's simple. In this model, everything's tough. And in fact, the model differences do matter, but not too much. So experience shows that, first, the fact that this is solved is fantastic. But secondly, the answers matches when you compare it to simulation. So actually, it works very well. The simple story is if we say this, in this model here, this understood to be, there's no Q here, but this is kind of a standard queuing thing. We're talking about the number of busy servers at time t in this thing. This has a simple distribution. Well, it might be. This is sitting there in Theorem 1 in the paper called Physics. At every time t, the number of busy servers is Poisson. Now, this right-hand side doesn't matter. It's Poisson with a mean that you can compute. That's the key idea, mental idea, not what the answer is, but that this thing is Poisson at each t and you can compute it. Okay? I mean, we'll come to, if we can, I'd like to come to why, but we'll get to that. That's the math part of this, which that's going to require it's going to require perseverance right up to the L time to get to that. It's going to require some perseverance. Okay, but the high-level story, I mean, this is, first of all, this is explicit, Poisson. But secondly, remember, a Poisson distribution has a single parameter, its mean. So actually, the distribution at all t is Poisson, and this, once you know this, that's all there is to know. I mean, whatever it is, don't worry about this. This is sitting there. There's a bunch of expressions for that. Now, what I should do to Steph is what you should all do if you think, what you're doing, what would I want to do? What is my response to how you should solve every problem? There's I'm constantly, every other day, every other class, I'm suggesting this solution to every problem. This paper actually is no exception. This research paper actually published is precisely suggesting exactly what I'm doing in class every time to this problem. Only we're going to get a time-dependent staffing. We're going to get S of t, time-dependent. Well, I'm thinking the numbers are moderately big, but they could be actually not too big, 1, 5, something. The number of servers you need might be 100. This is going to work great. Well, whenever I see this with 2 S's, depends on what do you think of, right? So one thought, you could think of fish, but anyway, you don't maybe not think of fish. What do you think about here? You think, oh, it's Poisson. What is it approximately going to be? It's going to be normal. Right? Poisson's approximately normal. So you do this. You staff at time t this way, and then this. Okay, now what am I doing? There's a bunch of things here. I staff this way. Why? At time t, the distribution is Poisson with some mean m of t. It's approximately normal then, with mean m of t. And variance m of t, because the Poisson mean and variance are equal, as I'm always doing, right? Just so mean is this, variance is this, square root's the standard deviation. I staff at 2 standard deviations above the mean. 2 standard deviations mean the probability of having to wait when you arrive is about 2%, because that's 2 standard deviations above the mean, roughly. I haven't gotten, you can fine-tune this, I assure you. You can think harder, that's kind of, if you're employed as at IEOR, you do this stuff, you think harder, but the main idea is right here. So you staff 2 standard deviations above the mean, and this little ceiling function to say, okay, it has to be an integer. We don't have 2/3 of an agent, so you pick the next integer above this, right? The next integer above whatever that real number is, and you staff at that level. And you do that as a function of time. And so you get staffing levels. So here's your, somehow this produces it at time, and if you have to fix the time, suppose you time, staffing intervals are like this. Well, maybe if this thing maybe produce something like this. I'm trying to draw what that thing would be. But suppose you have to make staff this. Well, you might staff by the max. This thing would lead this integer things, and it changes because it's got to go to integers. And then if you have to be staff in this staffing interval, constant, then you maybe pick the largest thing you need. That's to take care of the realistic, you can only change the staffing every 15 minutes, say. So you might take the longest thing you need, the biggest thing you need in it, 15 minutes to be safe. It would help to have questions, if there are any. There's the clouding. This time of class period has a certain fatigue. Just imagine, one thing I've resisted is the tradition of, there is a tradition of teaching our classes once a week. Which, yeah, you're like, oh my God. Like to take 3 hours straight, which seems inhumane, right? Okay, but anyway, that would be, imagine you had to sit here for 3, well, I guess we'd have a break for a few minutes, but anyway, it would be hard. Okay. Now, actually, you might, if you want to do better here, you might put beta here, and then your probability of having to wait, probability wait at t greater than 0 equals probability q of t greater than or s of t would be approximately, this is the tail of the normal, right, at beta. Beta standard deviations, right? Yeah, Rob.
M of t, is that the arrival rate?
No, m of t is what you get when you solve for the infinite server mean. Okay, and that's the formula. So the issue that there's 2 issues remaining that I want to discuss. One issue is what is m of t? And the other issue is how do you get the Poisson? Which are both, neither is too hard. But M of t, what it is, and what should it be approximately, is important. And there's a first order thing is, well, if it's stationary, what would the mean be? And that actually is an important issue. You want to be clear in your mind to understand this. There's an issue we've skipped over. What should M of t be in relation to lambda? And the answer, roughly, is if it was constant, that you'd have to multiply by the mean service time. And this is sort of, in a stationary model, the expected number of busy servers is this. And so the reference case might be this. This is called pointwise stationary approximation. You use the arrival rate at t times the mean service time, because in a stationary model, this is the mean number of busy servers. So in a non-stationary model, you just say, well, let's just do this arrival rate at t and do this. And that's a pointwise. And this reference point's very important. So actually, m and lambda, if the mean service time is something funny, aren't in the same scale. The two curves are you have to do this to make them comparable. And that's exactly what that's a totally reasonable response. You want to think about, how do I relate the m of t function to the lambda of t, and they're out of scale. You need to adjust by the mean service time. So that the m of t, but this is not the m of t. This is in the stationary, mg infinity, no t, and this is an approximation, but not the real thing. So the real thing's more complicated, but this story for the stationary model suggests this simple approximation, which is the reference case to think about the answer. Okay? So what's missing is, well, what is m of t actually, and why is it Poisson? Okay? Be of stout heart. We are going to get there. Yeah, Michael. Yeah.
So as opposed to calculating abandonment and arrival rate as a function of time and service time as a function of time, you just went through and assumed you had tons and tons of servers, and you found out how many you need at any given time. And
that would be analogous to, actually, we have a simulation. We have a procedure, kind of an advanced procedure, but that's sort of like what you might do. If you did that, this is what it's, if you found out how many you needed, that's sort of what's happening. It's not, but the thing that's different is, if you had tons of servers and found how many you needed, that's the idea. Imagine, this is the philosophy. Indeed, that's another way of thinking about it. Imagine first there are no constraints, no delays, no abandonment, none of this messy stuff occurring when the system's full. Just imagine you have your arrival rate, the customers come, they all go into service. That's the ideal model. Then say, from the perspective of no small deal, waiting, abandonment, all the messy things, forget the messy stuff. If you had all the servers in the world, how many would you need? And that's where this infinite server model is. And the point is, it's not just lambda of t. You have to figure out for the infinite server model, if you had all those servers, how many do you need? That's where the solution of the infinite server model comes in, to answer that question. But the philosophy is precisely that. The philosophy is, first imagine we had all the resources we need, all these servers, how many would we use? And then if you set so that a slack, that you're only going to, if you had all the servers you need and you're only going to be over the top by 2% of the time, you can imagine if you just set that there, that it's not going to make much difference. And it doesn't. Right? I mean, that point of view is, so it would be, you could in practice, if you actually could do this experiment, you might think, if I could just run this system, I have all these people, I could put them all there. And let's put in, I might need 100 servers, but I'm going to start and put in 300. Imagine they're there. And then you put the 300 people there, and you just see how many you use. And then you just say, I'm going to use that. Which would be, the only reason for doing this instead is that, well, you don't have those extra people to run this experiment. Right? But the idea, that's the philosophy, definitely. Okay. Now there's a simple story about why Poisson and why m of t in the form it is. And then there's more to be said, which I might, not sure, but anyway, let's see if we can do this part. There's a picture that's going to be drawn. So if you look at the physics paper, the picture is figure 1 on the third page. Or on the bottom of the 733. So there's these papers going around if you don't, but where did they go? That's not the papers there. They're somewhere floating around. We might have, maybe I'm wrong finally. I mean, okay, they're online. There's some there. Yeah. 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 Could you pick that up and pass? There's a couple of these things around. Are they empty? Oh, okay, we did get too many. They're online. It's online, and I will draw the picture. So don't fret. It's not necessary to see it in front of you, but it's easy. So the pictures really do the job always. Here we are at T. And what we want to do is look at how many customers are in the system, how many busy servers, how many customers are in the system at time T. So let's think about what happened in the past and whether they're there or not. So if we look in the past, we can plot backwards the times of arrivals, past arrivals. These are occurring according to a Poisson process, but with that funny time-dependent, non-homogeneous rate. But anyway, that stochastic part isn't going to matter at first. Then we want to know, these are when they arrived in the past. People arrived in them. This may go back arbitrarily far. Then let's think, how long are they going to be there? They're each going to get generated a service time according to the same distribution. So let's see what could be their typical service times. So suppose we put their service times this way. They have random service times, right, and so on. So this way are the times of arrivals, and this is the service times they all have. That's just a deterministic realization of what was generated from the randomness, right? Now let's say, who's there at time T? Well, remember, in this model, everybody enters service as soon as they arrive, right? As soon as they arrive, because it's infinitely many servers. So they all go into service immediately. So everybody's remaining work goes down at slope 1. This guy starts service immediately and is gone here. This guy starts service here and is gone here. Right? Because the guy arrived here, this was his service time. He enters service immediately, and slope 1, he's out. Gone here. This one's gone here, right? This one's gone here. He arrived here. His service time was this. He's being worked on immediately by one server, and he's gone here. So what's there at T is precisely these points that are in this triangle up here, right? The arrivals whose service times put them in this triangle will still be here at T. The ones that occur down here, the points that are down here, will be gone. So the question could be rephrased as, how many points are there in this triangle? The points are this way according to the arrival times and this way according to the service times. They're the ones that are there. Q of T is precisely the number of points in this triangle. Doesn't look like that's getting us too close, I guess, right? That may not, this part also is, okay, well, let's remember that this is Poisson this way, even though it's non-homogeneous rate. So let me do this picture. It'd be nice to have a different color. Here we have boom, 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 boom. So what I want to ask is, how many points are in this box? I want to find out how many points are in this triangle. But I'm going to ask how many points are in this rectangle. This is just an arbitrary rectangle. And what's its distribution? So the number of points that fall in this interval, I'm going to have this rate, the mean, is equal to, let's call that AB, AB. The rate is lambda of t. The number of points falling on the line here for a non-homogeneous Poisson process, which you will become expert on, section 5.4 something or other, is the integral of the time-dependent arrival rate over this interval. This is the mean. The mean number of points that have arrival times here is precisely this, the integral of the rate from A to B. Makes sense, right? Should make sense. The number of points on this line here is the integral of the rate. That's the mean. It's Poisson with that mean. Now what about in this rectangle? Well, they're in the rectangle, like this point here that's in the rectangle. If the service time, when the point is above, let's call this C and D, right? It's got to be above C but less than D to be in the rectangle. So that is, the probability of being in there is G of D minus G of C. Less than D, greater than C. That's a thinning. This Poisson variable has been thinned by this box independently. All these points are independent, and they're thinned by this. So the number in this box is Poisson. And the number in another box over here is Poisson. And if the boxes are disjoint, they're independent. If they're disjoint this way, this is independent of this. So the Poisson process, even though the thing's time-dependent, still has independent increments. And these service times are all independent and identically distributed. So the number of points in disjoint boxes are independent Poisson variables. That means that actually the distribution of points in this space is what is called a Poisson random measure. In any sets A, the number of points in A and B, the probability that the number of points in rectangle A is J and the number of points in rectangle B is K equals e to the minus ma to the j Poisson, right? And e to the minus mb k factorial. So if A and B are disjoint, the probability of distribution of points is independent Poisson variables, j and k, where the ma is the integral of lambda of t. You know, it's this. Just calculated. What that means is the number of points in the triangle is Poisson with the integral of the rate over this triangle. So that's where we get this Q of t. Q of t, I mean, it starts to be a little technical and fancy. Oh, I'm going to represent this triangle as the sum of a lot of these rectangles. It's kind of like calculus when you're trying to do. So the thing is, actually, this is Q of t is Poisson with m of t. The question is, what is m of t? Well, a little box here, that's the intensity, is what? If this is t, what's the intensity? Well, if this is u back before t, and then this is g, this point up. So let's see, maybe if I make it u this way, this is at time t minus u, right? If I go back time u, it's t minus u. So I would have lambda t minus u, and then this distance is, if I'm thinking of this as x, and this is t minus u, this would be g of x. That's the intensity of this point at height x and at time t minus u, because I have the arrival rate here and the density here. That's the intensity of a point here. I integrate that intensity over that triangle. That's the answer. Now, then what's the arithmetic tell you? I mean, that's the formula sitting there is what the arithmetic tells you. So when you do that, you're going to get, you could be going back, because the triangle goes way back, you're going to look at something. If you do the lambda t minus u, you're going to get, so that's to say, if I go, here is lambda t minus u, right here, this point, then at this point, since I've gone u back, I should go u up. And I'm in the triangle if the tail, if I'm up here above u. That's this. If I write it this way, it'd be better. That's just another, that's what this means. So this is being above u, and this is t minus u. So right, so this time here is t minus u, and then up here, this u, that means this part, this line is now above this point. That's this. And now instead of having an integral over the triangle, I've reduced it to a one integral that way. So I've got this formula, and that's the answer. And it's Poisson. So this is like, this thing is sort of artificial, made up Poisson random measure, but you might do a model like, what's the distribution of stars in the sky? And then you might say, oh, well, it's a three-dimensional Poisson random measure as a model, which may not fit very well. But I mean, you do. Or what is the distribution of raisins in an oatmeal cookie? Yeah. Or something. So different, that might be different sections have a certain number of raisins. A big oatmeal cookie, maybe, and you think about how many are here or there, it might be Poisson. Or you could think of the whole box of cookies, and if there is enough raisins. That's because I'm beginning to move the raisins and the, okay. I'm beginning to lose it, right? I'm beginning to think, well, yeah, lunch.
Yeah.
On the paper, you have it like, back if you have lambda of u and...
Yeah, you could do it in either order.
Either order.
Yeah, you'll see that. You'll see the high-level picture. This is where the high-level picture is you're going to have an intensity and a density, and you're going to integrate over that triangle. And so you could do it, change of variables, and do it in either order. Now, the interesting thing in the staffing paper, let me just say a little bit, is if you sort of start through this in a reasonable way, this is the staffing paper. I will give a 1-minute sort of summary of the staffing paper. You might take an example, and as some sinusoid thing is like this is given. There's an example given with a rival rate. I guess it's lambda of t is equal to 50 plus 30 sine t. And the mean service time is 1. It's concrete, but not too realistic. So it's going like this. And now the reference point is, I could think of staffing this in 2 ways besides this one. One way would say is forget this fluctuations, just take the average rate, right? And just staff according to the average rate. Another view is to say, well, I'm going to act at each time if I do the right stationary thing at this time and a different thing here. So if I do it each time, I'm going to staff somewhat above, and then down here, the staffing is going to be right above this. And if I take the average, I'm going to get some number here. Right? Those are 2 obvious reference cases where you need to think that I've got to factor the service time in there to get the right things, right? But I fixed, if this was an average arrival rate, I could staff according to that, or I could staff in a time-dependent way right above it. So I'm thinking I'm regarding this as the number of servers approximately, and not doing any averaging. The thing that the staffing paper is showing in this bad, hard example is if you do this average thing, or you do this time-dependent thing, which are the obvious simple approximations, it works very badly. On the other hand, when you do this infinite server thing, boom, it does a great job. So you'll see their pictures, they don't come out too well, of doing this 2 simple ways that don't work. And then the other way is producing some crazy staffing that's hard to even see. It's hard to believe the infinite server one, this is the staffing paper. Let me point, these are these crazy pictures first, but go to Figure 3, if you have the staffing paper. The figure shows that the staffing there's some very weird staffing function that's sitting in here like this in the middle of this cycle. I mean, it's fluctuating between 34 and 42, where the average one is 38 and the other two are doing crazy, totally different things. Nothing like the two extreme policies. This thing does something that you could never dream up just straight away, but it stabilizes. So what you can do if your performance goals are high, so the thing's not too overloaded, you can actually, in response to this time-varying demand, you can produce time-stable performance. Right? The system, I mean, this is kind of like a physics or electrical engineering problem. The demand, the arrival rate's totally crazy. And if you have your choice of staffing, you can make it so the probability of delay is nearly constant by staffing appropriately, which is sort of like that's kind of the goal. Okay, let's move to lunch. Have a good break.